This lecture is on energy and power. Let's start with a simple but imprecise definition of energy. That would be that energy is the capacity to effect change. This agrees with common understanding, but what kind of change? Physicists would say energy is the capacity to perform work. But of course, then you have to know what work is. So the physical definition of work is that it's equal to force times distance. A force is a push or pull. So in that sense, energy is the capacity to push things around, which is pretty much what we mean by effect change in the original definition. So what units do we use to measure energy? Well, force has units of pounds, or in the metric system, newtons. Distance you can measure in feet, or a metric system would be meters. So work and equivalently energy would be, in imperial units, would be foot-pounds, but in metric units we call that joules, but a joule is the same as a newton times a meter. And there are other units that are commonly used. A physical calorie is 4.2 joules. That's the energy to heat 1 gram of water by 1 degree Celsius. A food calorie is actually 1,000 physical calories. So that's 1 kilocalorie. A kilowatt hour, this is used mostly in electricity. A kilowatt hour is 3.6 million joules, or 3.6 megajoules. And that works out to about, you can round that off. Anyway, the kilowatt is 1,000 joules per second. A watt is a joule per second. And an hour is 3,600 seconds. So if you multiply it out, you get 3.6 million joules, or you can round that off to 4 million joules. A British thermal unit, BTU, is a little over 1,000 joules, which is about 250 physical calories. A quad is a quadrillion BTU. This is used in economic analysis. So it's 10 to the 15th BTU, or 10 to the 18th joules. So work is the conversion of energy into motion, or vice versa. And you can think of simple situations. Suppose you're jogging up the stairs. The chemical energy in your body is converted into a change in your altitude, which is your gravitational energy. So if we say work is force times distance, your gravitational energy is your weight, which is the force, multiplied by the height, which is the distance. When you drop an object, gravity does work on it and accelerates downward, moving faster and faster as it falls. So the gravitational energy is converted to what we call kinetic energy. That's the energy of motion. The kinetic energy is defined as 1/2 mass multiplied by the velocity squared. Okay, so notice that if we double an object's speed, the kinetic energy would be 4 times, it would be quadrupled. Okay, and similarly, if you're driving your car and you push the brakes with a constant braking force, if you doubled your speed, your stopping distance would also be 4 times, would be quadrupled. Okay, so double your speed means 4 times the stopping distance. Simple example here, if you think of a block falling on a spring, initially you have gravitational energy because you're up high at a certain altitude. As the object falls, that gravitational energy gets converted to kinetic energy, so it's energy of motion. Then if you compress the spring, then all that energy gets converted to what we call elastic energy, stored in the spring. And you can imagine this process repeating as the thing would bounce back up, get kinetic energy again, and then end up high with gravitational energy. So the catch here is there's all these different kinds of energy, but the total energy stays constant. We say that the energy is conserved. Okay, some types of energy, a more complete list here. So heat energy or thermal energy is basically a property of the material called its specific heat, multiplied by the mass, and then multiplied by whatever change of temperature will give you the change in heat energy. Gravitational energy, we said, is weight times height. Kinetic energy, 1/2 mass times velocity squared. And the elastic energy stored in a spring is 1/2 times the stiffness of the spring multiplied by the stretch squared. And then just sort of a little more complete list here. So we've got kinetic energies, the energy of bulk motion, gravitational energy, energy available by falling. Elastic energy is the energy of shape distortion. Thermal energy is actually the energy of microscopic motion of the atoms moving around. There's also electromagnetic energy, which we'll discuss later in the quarter. Radiant energy is the energy carried by waves. Chemical energy is actually microscopic electrical energy within the atoms. And nuclear energy is energy stored in the atomic nuclei. Okay, this is a table from the textbook. Gives some different forms of energy. We're actually looking at the energy per gram for various objects. And these are arranged in order from low density to high energy density. Notice a moving bullet has a fairly low energy per gram. Down the list here, batteries have low energy density. Even TNT, basically dynamite, actually has a fairly low energy density. But the catch there is that energy gets released very quickly. That's what makes it an explosion. Okay. So even things like chocolate chip cookies have more energy density than explosives. Okay, but the chocolate chip cookie, if you catch it on fire, burns rather slowly. Coal, of course, used for fuel. Butter, the preferred food of mountain climbers, has very high energy density. Alcohol, so gasoline, now you're talking about fuel. The reason these things are good for fuel is because they have high energy density. Okay, notice an asteroid, because it's moving so fast, 30 kilometers per second, when you do that 1/2 mass times velocity squared, you get a very high energy per gram. And then uranium, so the energy stored in atomic nuclei is more or less 1,000,000 times some of these other energy densities. So that's why atomic energy is doesn't require very much fuel. Okay, so the different types of energy are defined so that the total energy always stays the same. So keep that in mind. You can change energy from one type to another, but you can't destroy or create energy. So this is called conservation of energy, or the first law of thermodynamics. The more common meaning of the phrase energy conservation is the attempt to keep energy in forms which are useful. So useful forms are things like fuel and electricity, temperature differences. Those are more desirable than things like wasted heat and pollution. Okay, here's a list of various prices for energy from various sources, all converted to kilowatt hours. I think gasoline here assumes $3.50 a gallon. The price, of course, fluctuates quite a bit. So gasoline, about 25 cents per kilowatt hour. Coal, about 10 cents per kilowatt hour. Natural gas, even cheaper than coal, currently about 7 cents per kilowatt hour. Nuclear, around 11 cents per kilowatt hour, but I put a question mark because that really doesn't include the long-term storage costs of the nuclear waste byproducts. Somebody's going to have to pay for that. Hydroelectric, around 9 cents per kilowatt hour. Biomass, that's basically burning wood pulp for the most part, around 11 cents per kilowatt hour. Solar thermal electricity, that's where the sunlight is focused and used to generate heat to run, basically boil water and run turbines, just like is done with coal. That's actually quite expensive, 31 cents per kilowatt hour. Solar panels, down around 20 cents per kilowatt hour. And wind generation is around 10 cents per kilowatt hour. So notice wind is competitive with things like coal and natural gas, pretty comparable price. Solar is more expensive, but the price does keep dropping, so that's getting cheaper. Notice gasoline is actually quite expensive, so like even solar panels as a form of energy are competitive with gasoline. So if you buy an electric car and power it with solar panels, the fuel costs actually be comparable to the price of gasoline. Okay. I want to, I guess, update the analysis in the book about electric cars. I think it's his analysis is out of date and a little bit biased. Muller assumed a cost of $2.50 per gallon of gasoline, which actually today is probably reasonable, but it's recently been as high as $5 a gallon. So a more long-term average cost, probably about $3.50 is more reasonable. So his calculation using $3.50 per gallon would be 56 cents per kilowatt hour. If we compare with the, instead of comparing a Tesla, which is a luxury car, let's use something a little more practical like a Nissan Leaf, which has a range of 80 or actually nowadays more like 100 miles. So the point of an electric car is you can use it for commuting. It doesn't have to replace a gasoline car. So the battery costs actually nowadays around $5,500 for the battery. Capacity is 24 kilowatt hours. And if you assume 1,000 charges, like I think is what Muller was assuming. So even with the $6,500, 2,500 kilowatts per charge, 1,000 charges, that works out to about 27 cents per kilowatt hour instead of Muller's 56 cents. So, roughly half the price of what Muller concluded. And then you throw in the cost of electricity, you get 37 cents per kilowatt hour. So that's actually already cheaper than a gasoline car, at least at $3.50 per gallon. Plus electric cars, you don't have to do any maintenance. There's no oil changes or engine repairs. It's just an electric motor. You don't have to stop for gas. So actually has a lot of advantages over a gasoline car. Okay. This is just a little analysis looking at per capita energy usage. The annual average energy usage per person in the United States is about 3.2 times 10 to the 11th joules. And that's including, industrial usage, office buildings, everything. It's just the total energy used per year divided by the number of people. Okay, that's not just in your house. Okay, so if we divide that by 365 days, that's 890 megajoules per day. If you work out how many seconds in a day, that works out to 10 kilowatts or 10,000 joules per second. Okay, so 10 kilowatts. Let's compare that with the energy that your body uses. So if you have an input of 2,000 food calories or 2,000 kilocalories per day, that's 8.4 megajoules. Again, divide that by a number of seconds in a day. That works out to 100 watts. So your body uses energy at a rate of 100 watts, 100 joules per second, whereas the actual total energy usage per person is 10 kilowatts or 10,000 watts. So you look at that ratio, we use energy at a rate of 100 people. Okay, we use as much energy as 100 people. We each use as much energy as 100 people. So it's as if we had 100 servants at our disposal in terms of how much energy we use. Looking at it a different way, if we used food for all our energy, we would have to grow 100 times as much crops. And even just the addition now of ethanol, you may notice gasoline usually has some ethanol blended in. That's already actually affected the price of corn. Comparing different countries, if we look at how many gigajoules per person per year, that's what these numbers are. Look at places like Germany and Japan, which are modern industrial countries. So they're at 176, 169. United Kingdom, 164. And then the United States is basically double that, 327. So it would appear we have a lot of room for improvement in our energy efficiency. Okay, various energy sources and estimated supply. Oil, somewhere I came up with a number of 30 years. That's not till it runs out, but that's basically till it starts declining in availability. It's an estimate of when peak oil would happen. Okay, anyway, there's some pros and cons listed here. Oil, the big advantage is it's portable because it's a liquid. It can make it into gasoline. Some of the disadvantages, there's limited supply. We have to rely on foreign sources. Even though I think now the United States might be a net exporter. Prices are volatile, and also it causes pollution, including carbon dioxide, which is connected with the global warming phenomenon, which we'll discuss later in the quarter. Natural gas, which is mostly methane. Longer supply, but it's still going to run out eventually. It's inexpensive and clean compared to oil, but still does produce carbon dioxide and has a limited supply. Coal, there's plenty of coal for at least 100 years or more, but it's quite polluting. Also carbon dioxide, so global warming risk. There's risks associated with mining, and also if they do strip mining, it's harmful to the land. Nuclear energy, plenty of fuel available. It does not produce carbon dioxide, so it does not contribute to global warming. But nuclear plants are expensive. There's risk of radiation exposure, partly from mining and partly from the nuclear waste. And then there's a risk of proliferation because nuclear fuel can also be used to make bombs. Okay, hydroelectric power, it's renewable, it's inexpensive, it's clean, but there's just limited places where you can put dams, and they do harm the local habitat, especially for fish. Wind energy is renewable, it's clean, you don't pay for the fuel. The only disadvantage is it is a little bit expensive to make the wind towers. And there is some harm to wildlife, although it's actually much less than other threats to wildlife. So for example, you hear about birds getting killed by the wind turbines. I think the current statistic is that about 100 times as many birds die from flying into buildings as die from flying into wind generators. But of course, the more wind farms that we build, the more harm there will be to the wildlife. Solar panels, also renewable. There's no fuel cost. They're a little more expensive, which is the main drawback at this point. And biofuels, in a sense, they don't have direct CO2 because you just grow the plants and then burn them. But it can displace crops if you're trying to use, for example, corn to make ethanol. And there are indirect sources of carbon dioxide. For example, farmers, running their tractors would be burning fuel and producing carbon dioxide. Okay, so that's kind of an overview of our energy supply. Power is the rate of performing work. So the change, this little triangle means change. Change of work divided by the change of time gives you the power. It's measured in watts, which are joules per second. And you can compare, roughly speaking, a kilowatt, 1,000 watts is roughly a horsepower, 1.3 horsepower. Okay. So kilowatts goes to horsepowers. Table of power here for various tasks. This again from the textbook. So a flashlight, for example, is about a watt. We did that in the lab. 100 watts would be an old incandescent light bulb, might be 100 watts. And a human being is typically about 100 watts. A horsepower is roughly a kilowatt. You can generate a horsepower of work by running up the stairs. A kilowatt, another example would be maybe the combined appliances of a small house, all the lighting. 20 horsepower might be a small car. I think I earlier said, a big car would be more like 100 horsepower or 100 kilowatts. A megawatt might be a small town, or a 45 megawatts might be a jet airplane. A gigawatt is basically a power plant. 400 gigawatts is the average electrical power in the United States. And then 2 terawatts would be like the average electric power for the whole world. Okay, so that's some idea about power usage. Simple problem here. If you have 1,000 Newton, that's the weight, force of gravity. If you have a crate that weighs 1,000 newtons, and you lift it 2 meters per second, you lift it a total of 2 meters in 4 seconds, the work done, remember work is force times distance. So force is 1,000 newtons, distance is 2 meters. So that would be 2,000 joules. Newtons times meters is joules. And for the same forklift, lifting in 4 seconds. So power is the work divided by the time. So 2,000 joules divided by 4 seconds would be 500 watts. Okay, so here's a trick question. Which uses more power? Lifting 1,000 kilograms, which is called a metric ton, to a height of 2 meters in 20 seconds. Okay, or lifting 10 kilograms to a height of 2 meters in 0.2 seconds. So you've got 1/100th of the mass, but you're lifting it to the same height in 1/100th of the time. So the ratio there actually is going to come out the same. In both cases, it's 1,000 watts. But of course, the first one is more energy because you apply that power for a much longer time. Okay, so that's all for that lecture on energy.